Hey, this is Horner, and this is the second part of Chapter 3. This is probably the more important part of the two parts, and this one will really go into more detail into what you need to know. For Newton's second law, we know that a body accelerates whenever we have a net external force acting on that thing. So the acceleration that we have is proportional to the force, so the harder you push, the more acceleration you will have, and it also is in the direction in which that net force acts. So this law is commonly applied to the vertical component of velocity. So when we look at the up and down, we usually see this a little bit more. So here we've got the sum of the forces are equal to mass times acceleration, where the symbol here just means sum of, so that's the net force measured in newtons, m is mass in kilograms, and a is your acceleration. So we know that this whole thing is just solved for in newtons. So there are several steps here that you want to follow when you do a problem like this. It says Larry pushes a 20 kilogram block on a frictionless floor at a 45-degree angle below the horizontal with a force of 150 newtons, while Mo is pulling it with a force of 120. So they want to know, what is the acceleration of this block? One of the things that we have to realize about this block is there are two forces acting both up and down on the block. So we'd have the normal force and we'd have the force due to gravity on the block. But neither of those are in the direction of motion, which is to the right. And so because they're equal and opposite and they cancel each other out, we're only worried about the force of Mo. We also have to think about the force of Larry, and remember the force of Larry is both a downward force and a force to the right. So we're really only worried about the force acting in this x direction for it. So we could do a 45-degree angle here, and then we can go through and figure out what that side of that triangle is. So let's go ahead and move on through this one. So here's our force diagram, our free body diagram. We already said that we have the normal force up, the force due to gravity down, those cancel. Then we have the force to the right, and then we have the force down and to the right. So that's our free body diagram, is what we've seen. If you want to, you can also extend this one down to the right too, and then put in your 45-degree angle at this point. That way, when we solve for this side of the triangle, this would be FL times the cosine of that angle. So we'll do that here in just a second. For step 3, we set up our equations. So we know we need the force in the x and the force in the y. That's for more two-dimensional problems. We're going to split it up into two one-dimensional problems. We're going to substitute everything in, so make a list of givens, substitute in what we know, and then finally just go through and solve by plug and chug, calculate my unknowns, and sometimes I'll need to use what we call kinematic calculations, and we'll talk about those next. So there are some forces that do act as accelerating forces. Probably the most commonly known one is gravity. So you speed up as you fall up to a certain point. So that's gravity in action. And we say that that acceleration is g. And we've talked about what it is. In the absence of air resistance, you would just keep falling. But with air resistance, those things kind of go away a little bit as we go through. The pulley here lets us use gravity in order to be an accelerating force, but it doesn't accelerate this at the full amount of gravity. So we'll take a look at it again later. Let's go back to our problem again, and we've got that block. Let's go ahead and solve for this. We'll do our free body diagram again. So we know that we've got the force pulling down, which is the force due to gravity, force up, which is the normal force. We've got a force going to the right, which is the force of Mo, and then we have that 45-degree force of Larry. So we're going to actually put it here. And then let's find the components of that force. So to find the components of that force, we know that we can find a y, but we're really more interested in the x component here, because that x component is the one that will help us figure out, oops, this is Mo, how much force there is net going to the right. From that, we can then also find the acceleration. So let's go ahead and take a look. We know that this arrow pointing down to the right is 150 newtons. and the one that is pointing just to the right is 120 newtons. We want to know the sum of the forces in the x direction. So that would be the force of Mo plus the force of Larry in the x direction. The force of Mo we said was 120 newtons. Plus, we're going to do the force of Larry in that x direction. So here is our angle right here. We're going to find this, which is going to be the same as using the angle here. So you could use either angle. They're both 45 degrees. To do this, we're going to say this is 150. So we're looking at this side of the triangle. So that would be 150. So 150 times the cosine of 45 degrees. Times the cosine of 45 degrees. Now we can find out what the sum of the forces are in that x direction. So we're going to take 150 times the cosine of 45 degrees, and that would give me 106. So this is 120 plus 106, and if you add the two together, we get 226 newtons. So that's the force in the x direction. Our problem is we don't just want the force in the x direction, they also want us to find the acceleration. And earlier we said acceleration is equal to the sum of the forces, which we just solved for, divided by the mass. The sum of the forces is 226 newtons, and we're going to divide that by the mass, which is 20 kilograms. And that will give us our acceleration in newtons per kilogram or meter per second squared. So 226 divided by 20 will give me 11.3 newtons per kilogram, but in standard units that'd be 11.3 meters per second squared. So there's our acceleration. Next thing they're going to have us do is find what is the normal force. So notice not only do I have an x component to Larry's push, I also have a y component, and that's 150 times the sine of 45. So there's actually three forces in the y direction. And we know that the sum of all those forces in the y direction should be equal to 0. And those are equal to the normal force, which is up, minus that 150 times the sine of 45, minus the force due to gravity, because that force due to gravity is also pointing down. If I go ahead and move this Fn to the other side, that makes all of them negative. So negative Fn is equal to negative 150 sine of 45 minus Fg. So we can make all these positive now. So now our normal force is just going to be equal to 106, that's 150 sine of 45. It's the same as 150 times the cosine of 45 plus, and then remember Fg is just weight, and weight is just equal to mass times gravity. So our mass here is 20 kilograms. We're going to multiply times our value that we use for gravity, which is about 10 meters per second squared. Now we know that the normal force is about 306 newtons, and it is pointing in the up direction. So that is the normal force. Let's go ahead and take a look at the next thing that we have in this problem. We have example 3.8. The wheels fall off of poor Beatrice's suitcase, so she ties a rope to it, super heavy I guess, and drags it across the floor at the airport. The rope makes a 40-degree angle, the suitcase has a mass of 36, and she pulls on it with a force of approximately 65 newtons. They have several things they want us to find. They want us to find the magnitude of the normal force. They give us kinetic friction, so they want us to find the frictional force. They tell us that they want us to find the acceleration if she pulls with that force at this angle. And then if we start from rest, they want to know how long must she pull with this force before it reaches a comfortable walking speed of 0.5 meters per second. So let's go ahead and tackle each one of these things. First thing we've done is we do have a free body diagram here. This F sine of the angle and F cosine of the angle comes from the fact that we're thinking about that force that she's pulling with coming in this direction. So there are two sides to that triangle. We have our bottom side, which is going to be the F times the cosine of 40 degrees, and then our opposite side here, which is F times the sine of 40 degrees. So that should help a little bit kind of see what's going on. They want us to go through, remember, in A and find the magnitude of the normal force. So we're looking for N. So we're going to say the sum of the forces in the y direction should be equal to N. minus mg, and then we also have plus f times the sine of 40 degrees. So we know that the normal force is up. We see f sine of 40 degrees is also up, and then pointing down is mg, and so they've made it negative for us already. So we could either say we're adding the negative or we're just subtracting off the force that's going in the down direction. Because this thing is not accelerating up, we're going to say that all those forces are equal to 0. At this point, we're going to say we know that the normal force should be equal to mg minus f times the sine of 40 degrees. So here we've got the force times the sine of 40. Here we've got mg. Our mass is 36 kilograms, and we want to multiply that times gravity, which is 10, minus the force she pulls with, which we said is 65 newtons, and we're going to multiply that times the sine of 40 degrees. When you do your math, this is 360 minus 42. 360 then minus 42 will give you about 318 newtons, and that would be the normal force acting in the upwards direction. So that would be our normal force. That's letter A. Letter B, C, and D are a little bit easier to do, so let's tackle letter B. Letter B, they just want to find what is the force due to kinetic friction, and that's, remember, just mu k times the normal force. So we're going to take 0.13 and we're going to multiply it times that 318. So 0.13 times 318 will give us 41 newtons. For letter C, they want to know what is the acceleration of the suitcase. So we're going to look at everything in the x direction. So let's go back and draw our free body diagram again. We said we have a force going in this direction. That was F times the cosine of 40 degrees, because remember we had our force going up like this. And then going to the left, we have the force of kinetic friction. And those are the only two forces we have to worry about in those two directions. So the sum of the forces here in the x direction should be equal to F times the cosine of 40 degrees, and then we're going to subtract off our Fk. The force we said was 65, so we're going to take 65 times the cosine of 40, and we're going to subtract off that force that we got earlier, which is 41 newtons. So if we do 65 times the cosine of 40 and then subtract 41, we end up with about somewhere around 8.8 newtons. And they want to know what is the acceleration of the suitcase. So the acceleration of the suitcase, remember, is just the sum of the forces divided by the mass. The sum of the forces here were about 8.8 newtons, and we're going to divide that by our mass of our suitcase, which is about 36 kilograms. So 8.8 divided by our 36 should give us about 0.24. And remember, that's meters per second squared is the standard unit that we want. The very last thing they wanted us to find was how long of a time must she pull with this force for the suitcase to get up to 0.5 meters per second. So our change in velocity here is just equal to the acceleration times the change in time, and we got that from acceleration is equal to velocity over time. Change in velocity over the change in time. And so if I want to know how long it takes, we can find the change in time is equal to the velocity over the acceleration. And so we've got 0.5 meters per second is how fast we want it to go. And we solved for acceleration earlier of 0.24 meters per second squared. Notice that when we get done, the meters cross off, one of the times cross off, and that's 1 over a second, which leaves us with a second. And we can just take 0.5 divided by 0.24, and we end up with about 2 seconds is the amount of time it takes for it to get up to that speed. And that is the end of this question. Let's go ahead and take a look at the next one. Here we've got a brick of mass 1 kilogram. It is sliding down a 30-degree incline. If the brick starts from rest, how fast is it moving when it reaches the roof, which is about 0.9 seconds later, and they want us to ignore friction. So here's a good free body diagram of everything that we have. We've drawn this before. Here we've got mg. We've got mg cosine of the angle pointing down, and then we've got mg sine of the angle. And notice that we've made down positive and up positive. So that's why this is negative and this one is positive. So let's find the sum of the forces in that x direction. So here's our thing that we have in the x direction. So that's equal to mg times the sine of 30 degrees. And then this is also equal not to 0 anymore, because now it's speeding up. We're going to say that this is equal to mass times the acceleration in the x. If we go through and we solve for this, we would say this is mg sine of the angle. Oops, well, we'll just go ahead and put sine of 30 is equal to mass times acceleration. Notice your masses are the same. So here our acceleration is just equal to g times the sine of the angle. Remember, they want us to figure out how fast this is going. So we know that the change in velocity is just equal to our acceleration times time. We know our time is 0.9 seconds. And so we're going to take our acceleration, which is g, so that'd be 10, times the sine of 30 degrees. So remember, acceleration is g times the sine of the angle. So here we'll just write this, g times the sine of the angle, and we're going to multiply that times time. So we're going to multiply this times 0.9 seconds. And when you get done, you will get something close to about 4.4 meters per second. And that's how fast this thing is moving as it's sliding down the roof.